Chapter 9 Chemical Quantities and Reactions. When we know the balanced chemical equation for a reaction, we can determine the mole and mass relationships between reactants and products. Then we use molar masses to calculate the quantities of substances used or produced in a particular reaction. We do much the same thing at home when we use a recipe to make a cake or add the right quantity of water to make soup. In the manufacturing of chemical compounds, side reactions decrease the percent of product obtained. From the actual amount of product, we can determine the percent yield for a reaction. Knowing how to determine the quantitative results of a chemical reaction is essential to chemists, engineers, pharmacists, respiratory therapists, and other scientists and health professionals. We will also look at the energy changes in a balanced chemical equation. A reaction is exothermic if it produces heat along with other products. A reaction is endothermic when it requires heat for the reaction. In the body, chemical reactions require energy when we need to produce large molecules such as protein and glycogen from smaller molecules. When chemical reactions in the body break down large molecules, energy is produced, which is stored in high energy compounds. Section 9.1 Mole relationships in chemical equations. In any chemical equation, the total amount of matter in the reactant is equal to the total amount of matter in the products. Thus, the total mass of all reactants must be equal to the total mass of all the products. This is known as the law of conservation of mass, which states that there is no change in the total mass of the substances reacting in a balanced chemical equation. Thus, no material is lost or gained as original substances are changed to new substances. In the chemical reaction of silver and sulfur, the mass of the reactants is the same as the mass of the product. For example, tarnish, silver sulfide, forms when silver reacts with sulfur to form silver sulfide. 2Ag plus S yields Ag2S. In this reaction, the number of silver atoms that react is twice the number of sulfur atoms. When 200 silver atoms react, 100 sulfur atoms are required. However, in the actual chemical reaction, many more atoms of both silver and sulfur would react. If we're dealing with molar amounts, then the coefficients in the equation can be interpreted in terms of moles. Thus, 2 moles of silver react with 1 mole of sulfur to produce 1 mole of silver sulfide. Because the molar mass of each can be determined, the moles of silver, sulfur, and silver sulfide can be stated in terms of mass in grams of each. Thus, 215.8 grams of silver and 32.1 grams of sulfur react to form 247.9 grams of silver sulfide. The total mass of reactants, 247.9, is equal to the mass of the product, 247.9 grams. The various ways in which chemical equations can be interpreted are seen in Table 9.1. Information available from a balanced equation. Reactants: 2 silver atoms, solid, 1 sulfur atom, solid. Products: Ag2S, solid. 2 silver atoms, 1 sulfur atom, 1 silver sulfide formula unit. 200 silver atoms, 100 sulfur atoms, 100 silver sulfide formula units. 2 times Avogadro number of silver atoms plus 1 times Avogadro's number of sulfur atoms is 1 Avogadro's number of silver sulfide formula units. 2 moles of silver, 1 mole of sulfide, 1 mole of silver sulfide. 2 times the mass of 107.9 of silver plus 1 of 32.1 grams of sulfur yields 1 of 247.9 grams of silver sulfide. Total mass is equal. Mole-to-mole factors from a balanced equation. When iron reacts with sulfur, the product is iron 3 sulfide. 2 iron plus 3 sulfur yields iron 2 sulfide. Iron 3 sulfide. From the balanced equation, we see that 2 moles of iron reacts with 3 moles of sulfur to form 1 mole of iron 3 sulfide. Actually, any mole of amount of iron or sulfur may be used, but the ratio of iron reacting with sulfur is always the same. From the coefficients, we can write a mole-to-mole factors between reactants and products. The coefficient used in the mole-to-mole factors are exact numbers. They do not limit the number of significant figures. So 2 moles of iron to 3 moles of sulfur, or 3 moles of sulfur to 2 moles of iron. 2 moles of iron to 1 mole of iron 3 sulfide, 1 mole of iron 3 sulfide to 2 moles of iron, 3 moles of sulfur to 1 mole of iron 3 sulfide, 1 mole of iron 3 sulfide to 3 moles of sulfur. Using mole-to-mole factors in calculations. Whenever you prepare a recipe, adjust an engine for the proper mixture of fuel and air, or prepare medicines in a pharmaceutical laboratory, you need to know the proper amounts of reactants to use and how much of the product will form. Now that we've written all the possible conversion factors for the balanced equation of 2 iron plus 3 sulfur yields iron 3 sulfide, we will use these mole-to-mole factors in a chemical calculation in sample problem 9.1.